Hi everybody, it's Mrs. Peachy from Physical Science class, and I am going to have a short tutorial on covalent compounds and how to write the Lewis dot structures for them. So I'd like to, as usual, turn you to my handy dandy notebook. Let's go ahead and aim the camera down here so you can kind of see what I got going on. And I'm going to make the screen as big as I can so that you can see this a bit better. So, unlike an ionic compound, a covalent compound this is where electrons are shared. Because if you remember, we talked somewhat about this last time, that 8 is great. So all atoms want to have 8 electrons in their valence shells, but all atoms don't. And in order to achieve this stable configuration, they will either get rid of some electrons or gain some electrons, or in some cases they will share electrons in order to make that stable configuration. And this happens with bonding. So one thing I failed to mention in the last tutorial was that when we have ionic bonds typically are bonds between metals and nonmetals, right? Because if you remember, metals are positively charged and nonmetals are negatively charged. And we always write them with a positive charge first. So it's always going to be positive charged ion and the negative charged ion. That's how you would write them and that's how you would read them. Covalent compounds come when you're trying to bond two nonmetals together. Okay? So two nonmetals are bonded together, or a metalloid and a nonmetal, and so the charges are not going to really agree with each other. You're going to have like charged ions, so that doesn't work out real well. So to avoid that situation, they share electrons between them. Because remember, 8 is great. So that's the goal here, is to share electrons. I have a few different molecules written up here, different covalent compounds. Silicon dioxide, carbon monoxide, oxygen, diatomic oxygen, methane, and trihydrogen phosphide. Okay, so we have a bunch of different ones here. This one could also be called tetrahydrogen carbide, if you wanted to go that way. But it's also methane, aka natural gas. All right, so what we're going to do here is we're going to show how these atoms are going to share electrons, and through that process, we'll be writing Lewis dot structures for them. So let's start with looking at something called electronegativity. So I want to show you this screen here, and this is a periodic table, and it's kind of showing you a property of elements called electronegativity. And essentially, when you look at this scale, the closer it is to this light purple-blue color over here, the less electronegative it is. The closer it is to the hot pink and red, the more electronegative it is. And there is a trend on the periodic table that goes from less electrically negative to more electrically negative, with fluorine being the most electrically negative of all the elements on the periodic table. But you'll notice that chlorine and oxygen are pretty darn electrically negative themselves, okay? You'll even notice that there are some hot pink ones even in the noble gases. So that doesn't really, necessarily relate to the number of electrons. Electronegativity is the element's affinity for electrons. In other words, how much does it want to get electrons? Fluorine wants to get them really, really, really bad. So it's very electrically negative. And it would make sense that these guys over here that have just a few spots open would really want those electrons. Because remember, these guys are really trying to get rid of them. So they're the opposite almost of being electrically negative. They want to get rid of those electrons because it's much easier for them to do that. So when we're looking at writing these Lewis dot structures, And I'm going to go back to the screen here. When we're looking to write these this Lewis dot structures, what we want is we actually want to start with the atom that is the most electrically negative goes in the center if we have more than 2. Okay, so for silicon dioxide, we have 1 atom of silicon and 2 of oxygen. Oh, excuse me, the least electrically negative goes in the center. The least electrically negative goes in the center. Excuse me. All right, so in this case, going back to the screen here, we'll notice that silicon is less electrically negative than fluorine. So silicon is going to go in the center. Oh, we have oxygen. Silicon is less electrically negative than oxygen, so silicon goes in the center, and it is surrounded by oxygen. Okay, so let's do this. Let's put silicon in the center, and let's put oxygen on either side. Okay, so we know that that's true. Now we got to count up the number of valence electrons that we have here. So let's go to my periodic table. Here is silicon, and silicon has 4 valence electrons. So we start off with 4. Oxygen has 6 valence electrons, and we've got 2 of them. So we'll add those together. 12 plus 4 is 16 total valence electrons. So now this molecule is going to share those 16. And remember that the magic number is 8. So it's important that all of them have 8 around them in some way, shape, or form. So the easiest place to start is between the silicon and the oxygen. Now, in this case, electrons tend to form pairs. So we put those 2 on either side of the silicon. Okay, those are the 2 that shows us 1 bonding pair. That gives us 14 more. And if you notice that silicon now has 4 electrons around it, so it really only needs 4 more. Okay, if I add 4 more to silicon, maybe it would work best if I put them between the silicon and the oxygen again. Now silicon has 8 and each oxygen has 4. That means each oxygen just needs 4 more. Okay, so I did another 2 here. Oh, I'm sorry, what did I do? Another 4 here, so that gives us 10. Actually, I should probably just start over on this whole thing because I used 4 to begin with, so that would give us 12. And another 4, which gives us 8 remainder. And if I put 1, 2, 3, 4, and 1, 2, 3, 4, that gives us down to 0 left. So I was able to distribute them so that each one is going to have 8. See, there's 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then silicon has 1, 2, 3, 4, 5, 6, 7, 8. Okay? Now you might ask, how did I know to put the double ones in between? And it just kind of comes from experience. When you've done this a number of times, you know which number of total electrons are going to kind of lead to which configurations. But a lot of times it's going to be through trial and error. You're going to put a bunch of electrons out here, and then it's not going to work. And then you're going to figure out that it actually looks like this. So when you write this out, wherever you've got 2 electrons between 2 different atoms, that creates a single bond. So there's a single bond right here and here as well. Okay? And then there's going to be another one here. So you can actually write this like that. It's double bonded, and then you've got those 4 extra electrons on each of the oxygen atoms. Okay? Okay, let's do another one. Let's do oxygen, diatomic oxygen, O2. So there's nothing in the center, so we don't have to worry about electronegativity. We're just going to write our two oxygens. We're going to remember that oxygen has 6 valence electrons for each one. How did I remember that one? Well, we just did it. But if I look up oxygen, there's a 6 above it. So that gives us a total of 12 valence electrons, right? So I get 12 valence electrons here. Each one needs 8. Obviously, 8 and 8 is 16, so that's not going to work. But they're going to share the 2 that come between them, right? They're going to share 2 of them. Oops, let me do that again. They're going to share 2 that come between them, so that's good. That's all right. So then they each need an additional, like 6 more to be able to balance. But if I already took 2 away, I don't have 6 more apiece. So that ain't going to work. So what I think I'll do is I'll put another double pair here. So now each of them already have 4. So again, that takes away 2 here. And that allows me to give each one 4 more, which I will do like here, 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 and here, here. Okay, so that gives me a total of 8 around each one. 4 plus 4, and 4 plus those 4 here. Okay, which also means that oxygen is another double bonded element. There are some that don't have double bonds. So let's look at methane, CH4. Using my chart that I had before, we can see compared to, well, this one's a bit tricky, so let me just give you this one. Carbon actually is more electrically negative than hydrogen, but hydrogen's funky. Hydrogen pretty much always comes on the outside. Okay, so it's a little different with hydrogen because it only has the 1 valence electron. Okay, that one's just a little bit different. Sometimes they don't always exactly follow the rules. The rules are, they're meant to be broken occasionally. So we have our CH4, and I'm just going to switch pages so we have more screen. So carbon, if we look at the periodic table, has 4 electrons for carbon. Okay. Oxygen each has, hydrogen each has 1. So we have 4 hydrogens. And they each have 1. So we add those together to get a total of 8 valence electrons. So I'm going to write CH4 kind of just like this. Okay, with the hydrogens kind of surrounding the carbon. And I only have 8 valence electrons to share among everything. Remember, hydrogen's kind of a funky one. Hydrogen doesn't really need 8 electrons because hydrogen is one where it only has 1 or 2 spots, really, because it's just got that first shell. So if I put 2 in between each one here, carbon will have its full 8, and hydrogen, just has that 1 bonding pair. So this is what our Lewis dot structure ends up looking like for methane. Single bond in this case instead of a double bond. Okay? So those are some examples of covalent compounds and Lewis dot structures. If you have any questions or concerns or would like to go through some more samples together, then you can give me a call at extension 2204 or feel free to send me a webmail message. Have a great day, physical science students.